Hey everyone, this is my Physics 2 final exam summary video. I thought it'd be a good way to use this as a method to study myself and also help other people get some studying done or just review the content that they already know. So first, in chapter 16, we're going to talk about electric forces and fields. Okay, I'm just going to call this chapter 1. So basically the most important thing here is to really introduce the student to the properties of charge. So we can have a positive charge or a negative charge, and these can either repel each other or attract each other. Like repels like, and unlike is going to attract one another. So if you have two positive charges, for example, then they're going to repel each other. Another important thing is that charge is conserved. So this means that, for example, if you have a glass rod and a silk cloth, the charge before you rub it together and the charge after you rub it together, it's going to be the same. What do we measure charge with? Well, the SI unit is a Coulomb. That's all that I find important in the first subsection. So let's talk about the second subsection now, and that's electric conductors and insulators. So we have three different types of materials which vary in how easy or difficult it is for a charge to move. So we have a conductor. A conductor is basically something that is really easy for charge to move. An insulator, which is really difficult for charge to move, and a semiconductor. So these are the three different types of materials that are important here. And so what else do I want to say? I think that's pretty much it for the subsection. They talk about 4 different ways to use these. For example, number 1, charging insulators by rubbing, 2, charging conductors by contact, 3, grounding a conductor, and 4, charging a conductor by induction. But I don't think it's something that will necessarily be asked on an exam to explain it, but rather I think it's something that we should just know and use it as something that where we can just apply the principles to understand those phenomena. Okay, so that's basically all I want to say about the second subsection. The third subsection I think is really important, and I think it's something that could possibly show up on the exam. So here we talk about Coulomb's law. Okay, so Coulomb's law gives the electric force acting between 2 charges. So what is Coulomb's law? Let's call this the magnitude of the force. It's K, which is a constant, 8.99 times 10 to the 9 Newton per meter squared over Coulomb squared, I think. Yeah, it's that. And it's basically, this is the constant, this is the first charge, the magnitude of the first charge, this is the magnitude of the second charge, and this is basically the distance between them two. So for example, we have one here, we will have one here, this is going to be Q1, this is going to be Q2, and this is the radius. So if you want to find the force between these 2 charges, you basically just plug in the numbers. For example, it would be like 6.0 microcoulombs or 7.0 microcoulombs. You basically plug it in and calculate it. However, it's important to note that we have to use SI units, so a common conversion you have to do or know is that 6.0 microcoulombs equals 6.0 times 10 to the negative 6 coulombs. Yeah, and then we plug it in. That's how we find the magnitude of the charge, and force is a vector though, right? So if we have a magnitude, we also will have a direction. So if you want to figure out the direction, we can just see here that they're going to attract each other because positive and negative attract each other, like I said earlier. So just the concept to review here is basically how to add vectors, because force is a vector. That's basically all I think is important in the third subsection. Okay, then we talk about the electric fields. So we're really just talking about all different types of charges right now. So this is the electric field. So basically they introduced this section by saying that a point charge in the vicinity of other charges. So we have a point charge here and it's in another there's another charge around, it's going to feel an electric force. Okay, so basically the force that it feels is Fe equals QE. I'm going to put an orange box around all the formulas, actually, just so I want to make it bolder. Just so it's easier to just pick up what you want to get out of this video. Okay, so that's the force, basically. And this is the force, this is the charge, and this is the electric field. What else do I want to say? The vector units are, SI units, are basically newtons per Coulomb. So basically the kind of questions that will be asked are something like, can you find the force or the electric field? And what you need to do is basically, most of the time, come up with a free body diagram and incorporate the different components of forces. So just draw a free body diagram, usually like this, or any other forces, and then you use this to figure out what Fe is. That's basically all. And then the next subsection is really about motion of a charge in an electric field. So this is an application of the electric field, and this is why I think it's important to just talk about it here, because this is where we see most or a bulk of the questions. So we have a positive charge plate, for example, and a negative charge plate. So an important property of the electric field is that it's going to start from the positive charge and it's going to go towards the negative charge. So this is the electric field line. Electric field lines are going to go from positive to negative, like I said, and here they're uniform, so it's going to be the same all around. It's going to be the same in here, same in here, and same in here, but I don't want to draw it right now because I want to draw a particle inside. So a point inside the field is going to experience a force of Fe equals QE, like I said, and many questions are going to ask you to find, for example, the acceleration, and how you do that is just use Newton's second law, which is F net equals ma, m for the mass in kilograms, and the acceleration in meters per second squared. And if you want to find the acceleration, you just gotta rearrange it, and F net from here, we know that it's QE over m, and that's the acceleration. So that's the type of thing that you'll be needing to solve in this subsection. All right, and the last subsection is Gauss's law. So let's say we have a bunch of charges, right? Like if we have so many charges, it's not really feasible to use Coulomb's law for everything, and it'll take way too long because forces are vectors. So to do the vector sum and just to break down everything in components, it's going to take forever. So what we want to do instead is use Gauss's law. Gauss's law, basically, I'm just going to write it in the most convenient form. It's really this part. Gauss's law really says that the charge inside something, the flux equals the charge inside something over a constant, which is epsilon naught. It's a number. Let me see if I can find the number, just so, I think it's 8.85 times 10 to the negative 12 Coulomb squared over Newton per meter squared. And the formula really just allows you to solve for either the flux or the charge or the area or the electric field. Oh, I erased it by accident. A note I want to say is that this theta value is the value that is normal to the surface. So if you have like a surface like that, normal to the surface, this is the surface and this is normal to the surface, and so theta is going to be like this value because it's normal to the surface. That's all I want to say about that. that's basically Gauss's law, and this whole chapter is really just an introduction to electric charge and the electric field, and just introduce a person to the basic formulas. That's all I have to say about chapter 16. Let's talk about chapter 17 now. Chapter 17 talks about electric potential. Okay, so I'm going to use a different color to divide each chapter. So electric potential energy, the first thing they really talk about here is that the electric potential energy is the energy that's stored in an electric field. Stored in an electric field. So the potential energy, I'm going to call delta U. Well, everyone calls it delta U, but it's delta U equals to negative of the work done by the electric field. Note, it's negative. So what is delta U, right? Delta U is, well, it really only matters the difference. So delta U is U final, so the potential energy in the final position minus potential energy in the initial position, and we just want to define the initial position as 0 just to keep things simple. So when things are infinitely far away, you can think of it being so far that it doesn't feel any kind of potential energy, and so the potential energy is just 0. Okay, so what is the potential energy, right? Like, we know the change of potential energy, so the potential energy is equal to K, the same constant as we saw in Coulomb's law, Q1, Q2, and R. That's the potential energy. So for this, though, you need to use the algebraic signs. This is really different from Coulomb's law because there we just use absolute values, but here you actually have to plug in, for example, if Q1 is negative 6.0 microcoulombs, you have to use the negative in the formula. And why you have to do that is because you can actually get the sign from the number you compute. If it's positive, that means that the electric force is repulsive. And if it's negative, it means that the electric force is attractive. Okay, so that's all for the first section that I want to talk about. Well, actually, no. There's one more thing I want to say. If there are more than 2 charges, then we need to add the potential energies of each. So if you have EUE, and you have 3 charges, for example, 1, 2, 3, Q1, Q2, Q3, then instead of using this formula here, you're going to use K, Q1, Q2, R12. So this would be like Q1, Q2. This is the radius between R12. Q1, Q3, R13, Q2, Q3, R23. And that's what you would be using. So you see the top example in orange, that's if there was like 2 charges only, but here we have 3 charges, so that's what we're going to use. If you have 3 charges or more than 3 charges, you just need to add the potential energy of each pair of the point charges. We want to make sure we don't double count those, so if you do Q1, Q3, don't do Q3 and Q1 because it's the same thing. The next thing that